So today's webinar is going to be about evolutionary algorithms. And before that, let me introduce myself first. Oops. So my name is Aman Agrawal. I'm an industrial designer. So right now I'm freelancing, and I have started my own design studio with a friend of mine. So if you want more information, you can go to gracedesign.com. And I'm really interested in computational design and how we can use computers to design better solutions. So feel free to check my Instagram, where I often share inspirational projects that I find around the design community, as well as some of my research works and experiments. So it's really fun over there, so do check it out. So this concept of evolutionary design was first introduced to me by Richard Dawkins, because I was reading one of his books by accident. It was called The Blind Watchmaker, and he went through all the fundamentals of evolution and how nature is capable of designing quote-unquote evolving novice solutions, which are far better than what a designer or an engineer can even, or even architect can even dream of. And there was always an inspirational projects that he shared during the course of the book, and one of it was called Biomorphs. And it was like a really simple computer program where you can actually create insects. It was just lines, curves, but you can evolve insects going through iterations and iterations. So that was like the first experience, and it was really eye-opening because I'm sure when I started looking more into the field of evolutionary algorithms and computational design, and there were a lot of already big changes happening around that time, and there were a lot of projects by like researchers like Peter J. Bentley, Golding, Carl Sims, one of the pioneers of evolutionary algorithms. So their work were really inspiring. So I started digging deeper, and so it was really interesting to see how you can design using a different strategy overall. So the basic concept is like how the Darwin taught us like how emergent and generative power of natural processes are capable of designing really efficient and a tough contender for any engineers we can bring in front. And it basically works by non-random survival of random variants. So there are random mutations happening in the gene pool, which can give either a beneficial aspect or a negative aspect to the survival of a living being. And the survival depends upon the fitness, upon the environment, upon its rivals, food resources, whatever fitness that determines if it's able to survive sufficiently enough to reproduce and pass on the genes. So extracting the core fundamentals of evolution, and then we are trying to extrapolate to design. So we can think the evolutionary process as a designer's tool. So this process is not like replacing or automating designers, for now at least. It's I think it's a really good tool that can help enhance the process of design itself for a designer. So we are going to see why evolution can be a good tool for designers. So for example, the first one is evolution is a general purpose solver So it's really simple, like the instructions are really simple and can be extrapolated to a vast variety of problems. For example, resource allocation, optimization, form finding, data processing, etc. We already have seen a lot of examples where this strategy has been used, and it does work. It gives even better results than what if you intentionally start to design. So it has been used in data mining, video games, especially in engineering, also in app design. We are going to see some examples later on. This is the new concept that well, it's not new, but it has been new to me at least. The biomimicry or biomimesis. I think if you are from industrial design or architecture background, they do give you an introductory course about biomimicry, so that you can understand how designers and architects and engineers are analyzing and studying nature, and then extrapolating the solutions that nature is capable of designing, and then using it to solve real world problems. So far evolution is the best designer because it can chisel out the perfect engineer, designer, architect's dreams. Well, architects itself. And the fourth one, which is also a really interesting concept, which is about memetics. So the theory of memetics says that we as humans are not creative at all, like we have nothing special, and whatever we design or whatever solutions we come up are actually memes, ideas floating around from brains to brains. And there are certain ideas that are themselves really powerful and can occupy more space in a population. So it's a bit weird concept, but it resembles a lot like genes. And you can see the resemblance, like how nature tweaks and can come up with different solutions. And the same way we are doing it, like we do iterations after iterations of refinement, changing, and you can see a really good similarity between how nature is designing and how we as humans are designing, like the overall aspect of it. So we are going to see a few examples of evolutionary process to design solutions. For example, this one is an antenna that was designed by the team at Ames Research Center, NASA. So they created an algorithm which just modified the lines and vectors and the length, and they started the algorithm, and the fitness or the goal of this algorithm was to design an antenna with the least deviation of signal possible. And they were able to generate really interesting solutions which outperformed their existing designs. I have linked all the papers and resources at the end, so I will copy and paste it after the live stream so you can go and check it out in depth. There was this I would call it art installation or living being, you could say, by Theo Jansen. And if you haven't watched it, it's really remarkable. Like, we were able to watch it in Madrid. They had an exposition, and it's really gigantic. So Theo Jansen used if you haven't watched it, like it's like a creature that crawls based upon a kind of mechanism that Theo Jansen evolved himself. So he used algorithms to define constraints and parameters, and then he left it to run, and at the end it gave him a result that was working a lot better than the previous proposed linkage mechanisms. So there is a really good video about how he designed it, and it's also in the link. You should definitely watch it. It's really interesting. There is this another project by Autodesk for Airbus where they designed, well, they evolved, I'm sorry, I'm using design, but it's evolved a frame that was partitioning between like the cabins, and they used evolutionary algorithms to come up with variations, and then this final solution was a lot lighter and could theoretically save airline industry millions of euros in fuel savings. So this is also a really practical use of how evolution is capable of coming up solutions that are even better than what we can do just like that. There was another project by Autodesk. So it was the Mars office, and it's more for architects and interior designers. So they provided a lot of parameters and came up with this building that is really well optimized for the sunlight, for the movement, interaction of the people, the orientation of the desk, and everything is really evolved, you could say, like the positioning of everything. And they also have a really well documented presentation about this. That's also in the link. You should also check it out. Okay, so what is evolutionary algorithms? Like, we have seen it, how it is used. So overall, it's just using the natural process and bringing it to digital world, trying to solve a problem. Okay, because in nature it's like it's optimizing, it's running faster, which is overall surviving. So here we would like to see how it works inside a computer. So we generally initialize. So we initialize in context of Grasshopper. We initialize with random genes, random numbers, random values. Remember, evolution works in genes level. So you always have to think about not the organism itself, but what's encoded in its DNA. So what you see here is the DNA of our design. And evolutionary algorithms are only gonna tinker these DNAs. They're not gonna interact with the organism itself, okay? So that's a thing to keep in mind. So we start with random DNA values. Then we map those DNA values, those parameters, to a physical form, okay? So that's called mapping, or converting the genotype, genes, to phenotypes. It's also, it can be also like the process of embryology, which is itself is a really complex topic and might be a really interesting topic of a webinar for future. So we start with random values, and then we map those values to a physical form. How that physical form happens, that we have to design. And then we evaluate those designs based upon a fitness function. So for example, if we want this object to have the highest surface area, we are going to evaluate its surface area. We can also evaluate volume. Anything that can be measured in numerical value, we can use it. Aesthetics, if you are able to give aesthetics a numerical value, even you can use evolutionary algorithms. And then we select the we rank and order the solutions, so the best are like on top and the worst are at the bottom, and we create like a gradient of best to worst possible organisms, possible solutions. And then we assign a probability that if you are on top, you have a higher probability of going and passing your genes to the next generation than if you are at the bottom. So there are different ways to create like mate them, so we are not going to get in depth right now for it, but the basic concept is like the higher you are, the better probability you have to pass your genes. And then we also have a mutation probability, like there is a really small chance that we can control obviously in computer, but in nature there's a really small chance that in the process of copying the DNA information an error could happen, and that will change the value of the nucleotides of DNA, a mutation, and that could give rise to, that could actually lead to, first of all, nothing, like it doesn't change anything. In most of the case it will be actually a bad thing because it might hamper a normal functionality of a gene, or in rare cases it can be actually beneficial, that modification, that mutation. So that's what we are going to for that reason we are going to introduce mutation, because if we don't introduce mutation, our gene pool remains really stagnant, like the information that it can hold is almost fixed. But if we introduce mutation, we increase the amount of new information that can be integrated into our gene pool. And that's how we have created our first generation of organisms. And after that, it's just repeat and repeat and repeat. So we just loop it. We don't need to initialize again with a random value, because we are going to take the last generation genes. Remember, genes, not the object itself. And then we are going to map it back and then do the same thing again and again. And if we have a condition that if certain amount of fitness is achieved, we can obviously end the solver. Inside Rhino, we are going to use Grasshopper, and inside Grasshopper we have a different sets of plugins that can mimic this evolutionary process. So we have Galapagos, Wallace, we have Biomorpher, Embryo, and Octopus. So there are a lot of options, even more. I'm just putting these because I know them. So a really good tool that I highly recommend is Biomorpher, because you can actually visualize it. I do have a past webinar where we discuss a bit about Biomorph, so if you are interested you can look at it. And but in this one we are just going to look at Galapagos. So let's fire up Rhino finally. Any doubts so far? Wait, any doubts so far? If you have any doubts, please write in the chat. Meanwhile, you open up Grasshopper and Rhino. There is a lag of like 5 to 10 seconds, so I might get your chat a bit later, so sorry if I don't reply at the moment. Would really appreciate if you are if you have any doubts or anything that you would like to clarify, that you would like me to clarify for what we have seen so far. I'm just gonna scroll through. initialize, mapping, evaluate, rank and order, kill and reproduce, mutate, and repeat. Are the initial genes also a numerical value? Yes. The initial genes are, so these number sliders are these components that Grasshopper designed for genes. They both are number sliders, more or less. The second one lets you create bulk number sliders. We are going to look more into it, but genes are basically information that will eventually result in the physical form of your design. So it can be like generally it should be numerical value. It can be anything else. It can be anything that can contain information. But inside Grasshopper, yes, it's gonna be number sliders. Okay, I think everything's fine so far. So let's start with Grasshopper. So in the first exercise, we are going to do a really simple script. Let's create a point. And let's create another point. For example, this is our, I'm going to go to the top view. So this is our starting point and this is our ending point. And we want to create a path in between these 2 points. Okay. Obviously in this case, we can like literally do it, but we are going to design an algorithm where it tries to find that path. So let's import these point inside Grasshopper environment. Set 1 point. Set 1 point. So this is our start. I'm going to add a bifocal so that you can see everything else. Okay. All right. And we are going to move this point in XY direction so that we can draw a line in between those 2 points. So let's say, for example, move X, Y, Z vector. We are not going to provide anything for Z because it's just 2D. And let's provide a numerical value between -20 and +20. Okay. I think we need more. So we need to provide negative maybe 100 and positive 100. All right. The same for the Y component. And as you can see, if we change the values, the points starts to move. And we are going to create a line in between these 2 points. So this is the first and this is the second point. Okay. All right. So here we have these 2 values, number sliders, and then we have a line at the end. So in a really small example, we can see and identify what are what. So these 2 values are going to be our genes. So this is the gene pool. This whole process of creating the organism is mapping, and the final line that you can see here is our phenotype or the end result. So the algorithm actually never interferes with this form. It only changes the gene pool. It can only change the gene pool, okay? Whatever happens later on is the byproduct of changes to the gene pool. So let's bring down Galapagos. So Galapagos is under the param tab, utility section, and we can bring down the Galapagos component. So far so good. Okay, so let's connect the gene pool to the genome. So see what happens. When I try to connect it, I cannot connect it. That's because the Galapagos component works the other way around. So you have to bring it from here and connect it to your number slider number 1, and using the shift key, connect it to the second number slider. Okay. That's the first step. The second step is the fitness parameter, because we provided the genomes, but the algorithm needs to evaluate if this solution is good or not. So on what basis it's going to evaluate? So let's say we want that the distance between this point and this point is the least amount possible. So we are going to create a distance component that measures the distance between this point, the point that is moved, and our end point. So as you can see, if we connect a panel, the distance right now is 70 millimeters almost, and as we change the values, you can see how this value changes. Perfect. So this distance is going to be the fitness value. So again, if we try to connect it like this, it's not going to let me. However, you need to do it like this. Perfect. So let's double click on the component, and you are introduced with a new tab. So here, whatever you're seeing are the parameters that we can control about our evolutionary algorithm. So right now, just leave everything else except the first parameter. So the algorithm is asking whether we want our fitness to maximize. That means if we want the distance between these 2 points to be maximum, or we want the distance between these 2 points to be minimum. So in this case, it's gonna be minimum. Perfect. Let's just leave it like that and go to the solver tab. Perfect. So this is the solver window, and make sure that we are using the evolutionary solver. So it's marked. By default, it's always marked. And let's just press start solver and see what happens. So as you can see, the distance is becoming less and less and less every time. So a lot has happened in a brief moment. So I'm going to press OK and change the parameters and start the solver again. Make sure the fitness is set to minimize. And right now we are going to click this button. So by pressing this button, it's going to show us all the genomes that are being designed. So let's press start. So now you can see all the lines that were being generated shown by the algorithm, and you can see how it slowly starts to converge into the solution. So as you can see here, I'm going to stop it for now. When we started, the distance was 17 millimeters. So the point was something like that. That's the best solution that was in the first generation. This one. And the algorithm took whatever made that line, so whatever values made that line as a good gene, and then tried modifying and creating variants in the next generation, in generation number 1. And again the same 2, 3, 4 and so on. And in the 14th generation, you can see that the distance between these 2 points have been reduced to almost 0. All right. Any doubts so far? Okay. Another really important thing to keep in mind. So right now, if you see that the solver, even if we let it run for a long period of time, is converging, but the best solution yet has been only 0.25. It is not approaching 0. And that has to do with the resolution of our DNA or the resolution of the gene of this design. So what do I mean by that? So let's stop it. So right now the lines are being created. As you can see, when I change it, it goes from here to here. So it was earlier here, 41, somewhere here, and in the next step it goes over there. So it jumps from this point to that point, and that's why whatever was the possible closest and that the algorithm could achieve with these 2 parameters is this point, and the solver worked really well. However, if you want our gene to have higher resolution, we need to convert these numbers into floating numbers. So let's double click on the slider and just click on the floating point numbers. So what it's going to do is it's going to introduce decimal points. So now, as you can see, earlier it was jumping from this point to that point. Is going to just, it can sweep through, like you have in between steps too. It's really obvious, but whenever we provide higher resolution, we also trade off the computation resources. So keep that in mind always. Use it where it's necessary, and we are going to do the same for the bottom values. Are there only max and min solutions? What do you mean by if there are only maximum and minimum solutions? Do you mean that in the algorithm it generates only maximum or minimum solutions? Because, for example, so this is the generation number 1. So the best solution is 7 millimeters. And if you press reinstate, it's going to show you here. You can double click. Oh no, in this you don't need. You have to press reinstate. And if you want to see the worst solution, you have to go at the bottom of the list and select and press reinstate. So that's the worst solution, obviously, because you can see the distance, and this is the best solution. However, you have all the in-between solutions. So it's not just max and min, but it's the whole gradient of the best and the worst and everything in between. And so what another thing that I kind of forgot to tell you guys is that the algorithm cannot go farther than -100 because we have limited it. And it's really important, even though it doesn't sound like really it's obvious points, but for now at least, computers are really or scientists find it really hard to create open-ended systems, and that has to do something with this. So what we are always going to do is we are going to limit from where to where our algorithm can search from, and that's how we limit the or we create a domain in which we want the algorithm to search from. Obviously we can make it higher, like -1000 and so on, like it can go even farther, but it's a waste of resources because the algorithm has to sort through these solutions, and it's gonna do it. Like even if we put like -1000 here also, and you can see like it's gonna do it without any issue. So you can see it's going to get shorter and shorter and shorter, and then there will be a time where a mutation will happen that will push the point on the other side, and that's gonna become the best solution possible and dominate the gene pool. So now you can see that our algorithm is getting better. So 0.3, 0.32, 0.25, 16, 13, 0.03. So that's, or even 0.02. So I think that's the 0.01. So yeah, it's almost getting to 0.005. So as you see also that if we introduce the decimal points, the resolution to search has also increased. However, it has also increased the workload for the algorithm. So we have to always keep in mind those two things. Okay, so that's like the basic essence of the evolutionary algorithm. Any doubts so far? Okay, so let's create a bit more complex system where we have, I'm going to copy it and paste it. Delete everything else. Okay. And also maybe delete this. Well, so I'm going to create yeah, so let's create a move component, connect it here, and create an X, Y, and Z parameter. And let's think like a problem. So let's say we have a box like that, and we have obstacles like this, maybe something like that, and something like that. So obviously you can see that there is no straight path. The algorithm has to search through this. Okay. Is there any specific is there any way to get a specific value in a range like this to this? Okay, good question. So I'm going to abandon a bit just a second and go back to this example. So you have to always think that the evolutionary algorithm will try to approach the distance. So let's say there is a component called absolute, I think. Yeah, sorry, it's true. So let's say you want the distance between, so you don't want the distance between the end point and the final point to be 0, but you want it to be, let's say, between around 10. So we can create a negative component and the value 10, and we divide, we subtract the distance by that value. So right now it's -9, and let's create an absolute component that is going to give always a positive value. So what does it mean? So let's say if I have a number slider between -50 and +50, so you can see it's always giving me in positive. As soon as I approach the value 10 that is equal to the desired value, it gives me a value of 0, and anything below it I have +60, and anything above it is also positive value because we connected the absolute. So now if I connect these as the fitness, so it will try to, so let's draw 10, a radius of 5, I think it should be. So right now it should converge somewhere here. Okay, let's turn on the solver. Oops. Is there a bug or something? Let's see. Sometimes the Galapagos component doesn't work well with a different kind of component, so I'm going to just create a mass addition component, which is nothing, it's just taking whatever is in input and giving me the same values on the output. I hope it should work. So we want to minimize it, and let's start the solver. So now I don't know what's happening, there is something wrong probably. Yeah, sorry, because I have to connect these with the distance. Human mistakes. Minimize. Let's start. Yeah, so now it should work. So I had like a fixed number slider that it was converging automatically to the value. So it should get somewhere around that circle. So as you can see, we are approaching, like we have already approached. If you want to see, you can click this button. Yeah, I think it was not, it was twice. Yeah, it was twice. It was radius. So it did, because it was something like that. So it did converge between the value that you provide here. Okay, perfect. There are a lot of strategies to create your fitness function. I'm going to show you an example really fast where we designed this project for our university. So you create a digital universe of 50 by 50 centimeters by 1 meter, and you populate it with points, and you create a rule that you can draw lines between those points, and you generate random solutions. In this case, we just selected whatever we felt that we liked it. So it was a manual selection, just like how earlier pigeons or dogs were bred. All right. And we constructed it, and later we created an algorithm because there was like a difference between these and what the computer generated, and to compensate the difference, we created this algorithm. So it looks really scary, and that's why we used to put it here, but it basically is comparing the distance between each vertices in the it's comparing the length of each rod in the real world and in the digital world, and trying to minimize the deflection between the length of these rods. So you have like around 30 rods, so you can imagine how complex the amount of information that the algorithm has to go through. So in this one, you can reach a solution like in 15-20 seconds. Here we had to leave it for like 2-3 hours, but it did manage to approximate pretty well. So this you see, this box is my fitness function. So it's basically taking the initial value that we had in the computer and the new value of that same rod, and then comparing it internally, and then providing a total value in combination with everything else, and that is what is going to give me my final fitness function. So there are a lot of creative ways that you can design the fitness function. There is a really good article, and to find and to read that article, you just have to double click on the component, and here you have fitness function. So you should definitely read all of these articles if you want to use more this plugin. It's by David Rutten, the guy who developed Grasshopper, and he had written a really like a detailed explanation of how to use Galapagos and evolutionary algorithms in general. Okay, so we were back to the previous example. Okay, so here we are going to start here, and we are going to create some points, random points, and then create a curve through those points. So one way to do that is creating -100 and +100 number slider. So as you can see, we have values that goes from here to there. Maybe we don't need that much. -50 and +60 is enough. Okay. And the same here. But we want to create like 6 control points. We can obviously copy and paste 6 times, and that would be done. But we are going to use the gene pool component that you can find under utilities, gene pool. So this is basically number slider, but here you can create like a lot of number sliders just by changing like you want 25 number sliders, you right here, and then boom, you have 25 number sliders. You want to change the minimum and maximum of all of them together, you can do it here. So you say -60.000, well, it's already in decimals, to +60. So here you have the numbers. We want only, let's say, 6 control points. So it's going to only give us 6 number values. And you connect it here. Let's create a copy and connect one for X, one for Y. Perfect. And you can also like right click and randomize it. Like if you want random values, you can randomize it, and so you can see like more or less what solutions might come up. All right. And let's create interpolate component that's gonna create a curve between these vertices. As you can see, if we just connect it here, it's going to skip this point, the initial point. So we are just going to create a merge component where we want the first point and after the rest of the points in the same list. And now we have this curve. All right. Perfect. So let's just basically run it once again, like early. We want the, so in this case, we want the end point of this curve. The end point is this one, so it's here, and this point we want the distance to be the list. So let's create a distance component. All right, and let's go back to Galapagos, bring down Galapagos and create a panel just to see everything. All right. Connect it here, and this is our gene pool. Perfect. So let's run it. So we want to minimize the distance between this point and that point. So you can see that the algorithm is just gonna care the distance between these 2 points. It doesn't care about the rest of the points. It's a byproduct that they are like that. Okay, the algorithm doesn't care that much. So we converged into this kind of curve that is like that. Perfect. So I'm going to stop it. So let's say we also want that the distance is the list, as well as the length of the curve itself is also really small. So let's create a length component that measures the length of the curve. So right now it's 372, but we want the length between the length of the curve to be the least as possible. So we are just going to create mass addition component, which is going to take the distance between these 2 points as well as the length and provide us a unified value, like the sub addition of these 2. Let's randomize, because if you don't randomize and if you start just with the past value, the solver is gonna take that initial value in the first generation, and it might create like dominance already in the first generation. So make sure to randomize every time before you start running the solver. So let's say we want to minimize both of those values. Remember, we have only provide, sorry, I didn't connect it. So always keep in mind that we are always providing only one value to the fitness input parameter. You cannot provide multiple, like you can only connect one. So let's double click and start. Meanwhile, if you guys have more doubts, please feel free to write it on the chat. So as we can see that the solver is trying to reduce the distance between the points as well as the length of the curve itself.
Who are you? I am the architect. I created the matrix.
So as you can see, it seems to be stuck at these values. So there is this button called add additional mutations to the population. So there is already an amount of mutation happening in the solver, but we can input additionally by pressing this button. So let's press this button 2-3 times. So as you can see, when we press it, you can see the gene pool expanded because there were a lot of different designs, and it even made our design better. Like you can see it going up now. So sometimes adding mutations might help you to jump that local minima. Okay, so now you can see it even got better, like 67. But you will say that why this point is not meeting with this point, and that's a logical question, obviously. But you also have to think that the solver is really clever in a way, in one way or the other. Well, it's not thinking intentionally, but so what we are doing is, let's say the distance between these 2 points are going to be, let's say, so the distance between these 2 points are length 50 millimeters. So whenever this curve is trying to go to that distance, the fitness value is actually decreasing because the length of the curve is increasing itself. Shrey is asking why would it not solve to a straight line. That's because as far as the algorithm has been able to iterate, it sees that whenever it's trying to approach that line, even though the distance is increasing, the length of the curve itself is increasing. And that's why the algorithm prefers either to sacrifice the length of the curve or the distance from the point of the curve. And here what we can do is we can create weightage. So let's say we want the effect of the distance to be more important than that of the length of the curve. We want that this point meets this point, and that's more important. So we can multiply whatever value comes out of it by a number, let's say 2.5 or a bit bigger number. The higher the number, the more importance distance between these 2 points are gonna be. And let's remove this one and add this one. So now you can see it's 240. So let's start the solver. Now it should converge a bit better. Or we might have to even increase the values. So as you can see now, it is at least trying to be closer than before. you have to think that the algorithm has no access to what's happening inside Rhino. It's only thinking in terms of just values of numbers, like just the algorithm can only see this. It's like you have your eyes closed, you cannot see anything, and you just have to push some buttons and expect that the result is good enough. And you are getting the signal, like the feedback in terms of fitness function, where when you are approaching a good solution, you are being told that, okay, you are going in good direction, but you actually cannot see what's happening actually on the canvas. And evolution also works more or less like that. It only works in the gene scale. And now you can see that it has converged almost to a straight line. However, it has some weird artifacts, and that's normal, because if you want a perfect solution, you can use the other parameter, which is simulated annealing, which is basically going through all the possible combinations that the algorithm can do with these parameters. But it's getting there. Okay, we are going to do you want to either, we can modify this script so that now if we see an intersection between this curve with any of these curves like that, it punishes the solver. So let's say I can do a really fast improvement. So there is a component in the X intersection panel where we are going to see solve intersection events for multiple curves. I think no, it's curve and curve. So the first curve is this one, our original curve, and the secondary curve are all these curves that we draw. So these, this and that. And here you can see like so it's intersecting in one point. You can see it here. So let's do list length, and to get only one list, we are just going to do flat so that we only have one list. So as you can see here, whenever we have one intersection, it says like that. If we have more than one, here you can see two intersections. Okay, perfect. All right, so we are doing an intersection between these curves, these curves of what we draw, and then this original curve. And whenever there is an intersection, we are measuring how many times there is an intersection, and we are just calculating how many intersection points are there. And let's multiply this value. So if there is one intersection, we want the value to be, let's say, 500. Like, we want this to be really important. And I'm going to connect it here also. So right now, even though this solution was good enough before, after connecting this parameter to our fitness goal, it becomes a really bad solution because it's already like around 500 points. And when we set to minimize, the algorithm has to become 0 in order to get the best possible solution. So let's randomize it. And restart the solver. All right. As you can see, now it starts to work a bit slower than before. So it is slowly getting better. If you want the solver to work fast, just press either this one, where it's only gonna show the improvements. So meanwhile it's converging, let's talk a bit about what's happening here. So on the top we have the evolution of the evolutionary solver. So the top line is the best solution possible and the bottom is the worst. So you can see in the first generation there was a mixture of almost all kind of possible solutions, and as the generation has been going by, we can see there are improvements. So whenever there is like this point, you can see that a new species has taken over as the winning position in the past. Okay, so that's that. And the red line in between that you see is the line that's the average fitness of the whole generation. So the whole generation, the average fitness was somewhere here. However, now all the generation has converged to this solution where you only have one intersection point and it's a dead end, so nothing can be done. We can try mutating it, so let's press a few times mutation and see if some coincidence happens and we get some better results. No luck, so let's stop it and let's randomize it and start again. Sometimes it might happen that you are like, okay, it's getting stuck. So we are going to change another parameter. So when we start Galapagos, we want to minimize the fitness, blah blah blah. We can define how long we want it to run. So let's say it's a complex solver and you just want it to run for the midnight, and you set 6 hours and that's it. So you can run it and in 6 hours it's gonna stop. And we are going to look at this part. So this one is called initial boost. So remember when we were talking about here, so we start with a random population of genes. So here what we can do is, even though in this case 1 2 3 4 5 6 there are 36 solutions, we can say that the first generation, the generation 0, can have 72 solutions, so that it covers a vast possible solutions in the fitness landscape. And this gives us better chance that a good solution might happen. So we can increase that initial boost. So right now the max population is 50 designs. So let's and the first generation is twice, so it's 100. We can say let's do 200 designs in the first generation. So let's start it. Obviously it's gonna take a lot longer to generate the first generation. However, after that it's gonna be the same, but with the condition that now we have 200 initial random values that we can start working from. So as you can see that we are slightly better. However, I don't know if it's a good direction of solution or not. So we have to see. It might happen that we have really broad search area, and if we reduce the search area a bit, it might work a bit better. So we did get a breakthrough here, but we have to see how the solver managed to solve it. So we can see it here. So it is trying to maybe go through this way, because maybe when it was starting to go this way, it was always encountering this obstacle. So I'm going to introduce a few mutations and see if it works. So yeah, it's trying to approach the point from this angle. And yeah, I mean, it's a bit tricky work to design systems for evolutionary algorithms, because you have to think in terms of nature. So if let's talk about the eye, like the human eye. So it's like an engineering marvel, but let's think about the initial stages of the vision development, and the goal, or sorry, the criteria for surviving was determined if you had a human like eye or not. So in a billion trillion years, you cannot evolve a human eye from scratch. What does it mean? It means that no vision was worse than at least any kind of vision. And what do I mean with that is, right now we have a static fitness function. So we are asking too much from the algorithm. So we kind of have to design it in such a way that we are increasing the complexity of the fitness slowly, or else we are putting really strong fitness parameters, and it might not work. It's gonna generate, like you can see, it's working, it's finding new ways. If you are going to apply these strategies, it can also help you generate forms that you could never even think of, but it might not be able to design the most optimum solution based upon the parameter just like that. And there has a lot work to be done, a lot to be learned also, how to design a system, an evolutionary system, where on one hand you have the development, how you translate genes to phenotype, and on the other hand how you evaluate these solutions, how you set up the fitness parameter. So yeah, and I mean, if you can leave it like it's getting better, like it's 714. However, I can say that it's gonna it's not gonna go further, because you have basically, if you go even further, you are going to collide with this or with this line, and it's gonna be really difficult now that the algorithm has converged so much to modify these points to go here. It's right now it's like saying an amphibian to grow wings, because we are really down in the evolutionary timeline that now asking them to fly, like amphibians, frogs to fly, is gonna be putting a really strong fitness pressure on them, and they won't be able to do that just like that. So you have to think in a way, like if you want to make some like a frog fly, I don't know if it's possible, because another thing that is a more complex issue that we might discuss in future webinars is that you need to also have the back-end architecture of generating those forms, but anyway, that's another issue. So yeah, you cannot provide really strong fitness values and expect that it's gonna work like that. We also have to do a lot to make our fitness function better. So in case of this example that I showed you earlier, we created like a gradient where it was not like bad results. Sorry, let me see if I can draw it somewhere. Yeah, maybe I can draw it here. But yeah, you can see it's getting a bit better. It's trying to straighten itself up. However, any movement now it's gonna make, it's more or less converged. So there is no hope for this organism. Another good example of such bad designs in nature is the giraffe nerve, I think it's called laryngeal nerve. And you can think that, so we have a nerve that goes from our brain right through our aortic arch and then to our vocal cord. So in the fish it was just a straight line from the brain, I think it's here. However, as we started evolving, this nerve got stretched and stretched and stretched, and you can think that now it's really hard for evolution to correct this, because it's really down in a rabbit hole. Because like if you intentionally design a giraffe, you basically connect this nerve there, like it's 2 to 3 inches or maximum 10 centimeters. However, it goes around here, and here it's almost like I think it was 8 meters or something like that. So that's how evolution can sometimes be dumb. But you also have to factor in that the sacrifices that it has to make this nerve go here is not worth than what is already there. So it works. That's what evolution is. It works. And here also, it's not trying to achieve the best solution possible. It's just trying to be better than what is in the gene pool. And that's evolutionary algorithms in a nutshell. There is another example that I wanted to go through. However, I think we are short on time. And I don't know how you guys might be bored, because this is not like the typical you do some parametric stuff and it's done, but it's a bit more getting into bits and nerves of evolutionary algorithm. But yeah, I would really like to know if you guys want to ask specific questions or something, or if you want me to change or go into 3D and not just do like a curve and point. We can do that too. I do have the file that I made for the webinar. It's here. So it's basically I'm going to hide everything else. So it's basically, we have a cylinder, open cylinder. We rebuild it using, can we do a 3D surface form as a result of this? I don't get what you are trying to say. Like, can we do a 3D surface? You need to elaborate a bit more, please. Okay, so here I'm going to link the file with the email, so you can experiment on your own, because we are a bit behind the timeline today. Sorry, I didn't calculate it properly. So basically what we are doing is we have the genes here, we have the phenotype here, and this is the process how the genes are translated into, these numbers are translated into this kind of geometry. Okay, so what's happening is we have a surface, we subdivide or rebuild the surface, and we extract the control points of the surface, and we are going to move these control points based upon the genes. Okay, so based upon these parameters, we are going to create lines like this, and then we are moving these points over there to create this geometry. Okay, so whenever I change any value, you can see how this is affecting the shape of the cylinder. Anyway, so we had, just a second, we have 350 points and we have 350 genomes. Well, it's fine. All right, and after that, so this is our surface. What I did here is just convert this surface into a mesh, because if I just connected an area component, because I wanted to know the surface area of this geometry, it was taking a lot longer than converting it into a mesh first and then taking the area of the mesh. So basically we are trying to achieve, so let's say this is going to be part of, so this is going to be part of a tubing system where we want the maximum surface area possible to dissipate the heat, and we just want to create a surface by modifying these control points that contains the maximum surface area possible. So let's say if I do like, so yeah, it's something like that, like the tubing, maybe an Arctic. Yeah. Anyway, so we have a tube like that, and let's see how it works. I'm also going to create a new environment so that we can see it properly. Okay. So we have a surface, and we subdivide it and we move the points to create this new surface, and then we get an area overall, which is this value, and that's our fitness. Perfect. Let's start Galapagos. We want the surface area to be maximized, and turn on the solver. Sorry, like always, don't forget to randomize, because your past solution might become the best solution of the first generation and dominate the gene pool. Okay, meanwhile it converges to some results. Any doubts, questions, recommendations? Because we are going to do a second part of this webinar where we are going to see two examples, one for architecture, like a real use of this algorithm, and one for industrial design. So if you have any suggestions or any idea that you would like to see, just write in the comment of the video or send me on Instagram, and we can make that happen. Yeah. So as you can see, the overall fitness is going down. which sounds unintuitive, but I think it might happen as these are control points. So whenever you are doing any kind of movements, you are actually cancelling out the undulations and might reduce the fitness function. That's why now it's slowly picking up. So whenever you feel that it's not getting better, you just try to do some random mutations, might get lucky. So yeah, we got a bump here. So yeah, I think it should get better, even because last time I ran it got almost 800 and something, like 14 or something. So there is a lot to improve, but you get the idea. So this is like the basic because it's not like this simple, because if we are going to do just like this simple, we are not going to get a good approximation of evolutionary process itself. So what we have to do is get as close as possible to nature to replicate this process. For example, right now the fitness is static, like there's only one final goal. However, as I told you earlier, we can do like incremental goals. So for example, in the exercise of the curves that I deleted, maybe what we could have done is we could have just we could have introduced either just one box first, and as the algorithm is running, as the evolution is happening, we introduce a second curve, and that's how you are slowly increasing the complexity of the fitness function, and the algorithm might work a lot better like that. Okay, so yeah, it kind of converged here. Let's bake it. So obviously, like the more undulation difference it can generate, the higher the surface area is going to be. I mean, obviously it's if we think we can just do like alternate, but we don't know if that's the best solution possible. Anyway, here, let's say we were going back to the previous example. So I would remove these curves and start the again, like early, reset and this time I'm going to reduce the distance by -50 or -20 to +50. Yeah, so a lot concentrated. And let's start the solver. Sorry. So we can see that it's a lot better now. It's not intersecting with any of these edge lines. So let's say we introduce now this to the equation. And let it run for a while until it gets a bit better. And then we introduce this as well. So now you can see that it's trying to adapt to the new conditions. Obviously, the first steps or the first genes that helped these curves to stay inside the box are there. They're there because they were good enough. They were good to keep the curve inside the box. So it's gonna retain those genes that will not let it go outside of the box, and now it has to work within the genes that it has to adapt to the new circumstances. So let's provide a bit of mutation, and yeah, we did get something here. Let's see if it's a good solution. So we can press this to see. So now you can see it found a new way that is closer to the curve, and now it's trying to reduce the length also. So this is what I meant by slowly increasing or leveling up the game. If we start really strong from the start, it's gonna be hard for it to emerge, because in the nature it's also like that. You don't get from single-celled organism to a lion or a cheetah or any organism that's alive. You have to go through like a scale, like evolution of the evolvability itself to guide the process. So you can see now it works a bit better. We can, well, these two curves were not doing anything previously, so they're not gonna even do anything now. But yeah, you can, oops, no. Now I can make sure you're on the first visualizing option, because that's how you will be able to interact, or else it's gonna stop completely Grasshopper. And when you see that it's not getting better, just maybe introduce a bit of mutation and see if it gets better. So I think it jumped suddenly to 118, so that was a good improvement. So now you see we don't need to like do huge improvements. We are doing small steps of improvements that is helping the solver to get to the goal. So yeah, that's gonna be for examples, that's gonna be, I do have some other things to go through. Yeah, so we have not covered a lot of topics. I know it's really, even if you are familiar with the evolutionary algorithms, you might even consider this as like, okay, I knew about it, but it was really simple, basic. But if you want more real world applications, let's do it. Either architecture or industrial design. Any examples that you would like to do, we can see how to make it happen. After that, I do have book recommendations, like always. So the first book is this one by Peter J. Bentley. So it's you can read it in the name. It's Evolutionary Design by Computers. It's a really good book on how the concept of evolutionary algorithms came about and how it is being used, etc. So it's a bit old. I think it's from 2000 somewhere, 1999. So it's it's almost 22 years old book, but nothing drastically has been changed so far. So it's really good handbook if you want to get more into in depth of how to create a proper evolutionary algorithm for industrial design or architecture or anything like that. Because here they explain in really like in a descriptive way how to do it properly, or at least give you idea of how to make the solver a lot better than just simply connecting everything and just connecting the fitness function and expecting a result. So a lot more has to go into how to make it work, or a lot has to be learned from nature and just try to replicate it inside the computer environment. And the next book is the Meme Machine. So this was the book that provoked, well, it's from Susan Blackmore. She was, I think, colleague of Richard Dawkins, and we also have a foreword by him. And they discuss about the concept of memes, not the internet memes obviously, but how ideas of design and everything are equally competitive as genes to take space in our minds, and a lot of more philosophical aspect to it. But the thing that really is interesting is how you are gonna see creativity after reading this book, and the creative process itself, and how if possible to take out the essence of the workings of memetics and implement it in architecture design, product design, industrial design, or any kind of problem solving questions. So it's really interesting book also. Anyway, I do have the links to the previous things that we saw. I'm gonna copy and paste it into maybe the description of the video. I think that's gonna be the best way for you to access it, and also with the email after the webinar. If you guys are interested in, well, now they're free, but if you guys are interested, you can get free Grasshopper files to experiment and learn. So this is for generative design, and I used Biomorph, so that's also really interesting plugin. And after that, yeah, so would really appreciate if you guys can fill up this form. It's a feedback form. If you guys liked the webinar, or anything to improve, you can mention it over there. Anyway, questions before we call it off for today? I'm gonna be active just in case anyone has any questions specifically with the exercises or anything that we saw here today. Feel free to write it in the comment section. Also, if you do make some designs or something with Galapagos, do share with me on Instagram. I will repost. I hope you guys liked it. I think seems that you guys don't have much questions right now, but I'm sure once you're gonna start using it, feel free to contact me. And that's it for today. Thank you very much, guys, and see you guys in the next webinar. I think it's gonna be maybe in 2 weeks, maybe. I'll keep you guys updated, but thank you very much. Bye bye.